So last Friday, you actually coded a neural network. Now, to start with that, I just wanted to get an input from you in terms of like what went good, what went bad, what you don't like, any things where you have some queries. Then we can resolve that before I move on to the next architecture, which is on Google Net. So are there any queries in respect of implementation which you would like to discuss?
Hello.
Yes.
Yes, so in the last class, when we are calculating the gradients, so
Mhm.
there was a problem. Like since we were trying to use GPUs, and we were in the code, we were implementing the entire batch gradient descent, not
Hmm.
mix batch. So it was most of us in our laptops was having some problem with that, because GPU in like an entire 60,000 data in one epoch to do the gradient is a lot for the GPU in our computer itself. So we had to change that.
Yeah, you were running on memory issues at that point of time. That is why we were discussing the space complexity.
Yes, sir, yes, sir.
The
So
point is that we have discussed space complexity only in the forward pass. We have
hmm,
not discussed the space complexity in the update part of it at all.
yes, sir.
I will come to that. In significantly large space to do a backward.
Yes, sir. So that's where the problem was coming. So we had to shift it to the mini batch.
Yeah, mini batch means a batch wise gradient descent. So
Exactly.
essentially you have a smaller batch size. There is nothing called
That's
as a mini batch. A mini batch means a very different thing. A mini batch means that your update happens once in a batch, but when you are doing all the piecewise calculations, then you even split that batch even further.
no, we were just using one batch for other updates.
You were doing a batch wise update in that case. Yeah, they come in learning rules essentially. The only problem is that I cannot finish everything in theory and then get you exposed to it. So
Yes, sir.
there will be some things you are getting to know. Now come to the okay. Anything further?
No, sir.
Sir, are we going to do the hyperparameter tuning?
Yeah, we will do all.
Yes.
We will do network architecture search. We'll do hyperparameter tuning. Everything is there. I'll get you introduced to the theory. We will then start doing it. The only word of caution is that hyperparameter tuning as well as network search, they are pretty like compute costly matters. So, and as a result of which, if you try running them on Colab, then the chances that your Colab session will expire before your experiment gets over is very high.
So in the last lab when we were doing like without GPU in and when we with the torch and the so our matplotlib were not working. When we are trying to plot something, my kernel was getting dead. It's just not me. Many of them. We were telling the our guide to do something, but they were telling about reducing the base size, but there was nothing to do with base size. It was there with torch
No,
and
wait, what was not working? Matplotlib.
yes, sir. With when we are, I'm regularly working with TensorFlow, sir. I first time I took this torch, and then when I'm using Matplotlib, it's getting kernel is getting dead with that.
Oh, then that's a issue with the if kernel is dying, then it's an issue within your environment.
Yes, sir.
We'll
That's why.
have
But
to do a
we
deep
had
dive
only
and check
base
it
environment,
because
sir. I didn't make any special environment for that. Root base.
no, it's not about you making a special environment or your root environment. There may be something which is associated with your hardware software configuration as a result of which it was having that problem. So we will have to do a deep dive into it.
Sir, it's just not about me, sir. There was many of them. The same problem, sir.
It's very much possible, my dear. It's very much possible. So we'll just do a deep dive and understand like what is the problem, and then we'll solve it. So we just need some more time. The point is that if it was in class, then it is much more easier to solve because I mean everybody is over there. Some
Yes.
TAs can sit and group all the people and then try to. But this is also a sort of like hidden trial method.
Yes.
Because we did not design the kernels or these engines or any of them, so we don't know. So we'll have to like sort of explore out what is the possible problem which is happening. But
So,
they are
before
solvable.
the first assignment, if we can do resolve this, then it will be better, sir. Otherwise, we won't be able to submit in within the time limit if you give
So did
something.
you tell your TAs about it?
Yes, sir. We told sir where we discussed like more than a half an hour after the class, after the
So
session.
then what you see, what I would suggest is in the MS Teams, not in the chat for the meeting, but in the general discussion forum in MS Teams, one of you actually create a post which is about the this Jupyter Notebook kernel during Matplotlib and share some screenshots of what is happening over there, and then so that we are able to recreate and also tell like what is your processor, what is your OS, what is the version of Jupyter Notebook which you have installed, what is the version of your Matplotlib. Then that makes it easier for us. We can go and take a look into it.
Okay, sir.
So we'll try to recreate it. We'll see everywhere. My Jupyter notebook is so old that I don't even remember. None of these problems will come. Maybe because of the newer versions or some clashes, these problems are over there. So that needs to be taken care of.
Sir,
Yes.
so while doing the same thing, like I also faced a problem. So I like you were saying, you need to install drivers for the GPU. So I uninstalled the Python itself and everything. And when I installed PyTorch, it was not even recognizing PyTorch. So what I did, I created a new environment, and from that command prompt, that Anaconda command prompt, I installed that like PyTorch. So it was like then there was no compatibility issue, because it was checking the version which was latest and which was compatible with the Python version I've selected for my environment. So that resolved everything for me.
Typically, problems are because of version mismatch and nothing other than that. And yeah, I mean, what you did is sort of like brute force what we would have done anyways. Though it's not always a good idea, but you can always another thing which works out. I think that is what we do, at least on our side, is we update packages. We update and upgrade so that everything is up to the line before we install this additional one. And also, like when you install the newer package, there used to be a macro called as fix missing. So if there are certain dependency packages which are not present over there within your Conda environment, then it can download them as well in order to fix it up. And a general advice, what I would give is, like, if you are doing on TensorFlow as well as you are doing on PyTorch, then create two different environments of Anaconda. One is purely for your TensorFlow environment, another is purely for your PyTorch environment. And like these conflicts go to a minimum. Even on our servers, when people do it, we have it like that. So we have even ONNX runtime environments, which are again created separately. Just that there is no conflict, because there are some versions up down which has to be done for all of them. Not everybody goes with the same versions.
Sir, which is better, like in Torch is better or TensorFlow is better, like in using terms?
So this is like you are asking me to endorse which one is better, which is critical. But then, I mean, we work more on. So PyTorch has its legacy from something called as Torch, which was based on another high-level language called as Lua, and that was taken care of by the Torch Foundation, and Facebook was supporting it for a longer period of time. And eventually, when Python started becoming very popular, and more of because TensorFlow was there, which was coming up so big on this one, Theano had already died by that point of time, and then there was a need that Torch itself gets supported on Python. So then the whole library was recompiled from scratch and made compliant with Python. That was how PyTorch came into existence. So a lot of us who used to work in Torch, we found it convenient to just move over to PyTorch. That was the point. And nothing more than, because we did not start deep learning when TensorFlow was there. We started deep learning way before that. I mean, my age of deep learning started when Theano was there, so that library does not is no more supported. Cafe was there, Cafe 1, and it was tremendously dangerous. Like, it was very hard to get it installed even. We're not even speaking about Cafe 2. So when we started from that point of time, then our automatic choice for a scalable thing which could do multi-GPU supports and everything was Torch. In fact, like, we were the original contributors on the multi-GPU and multi-server support for Torch. That's something which came out of a lab. And when PyTorch came in, it was very natural for us to move. Couple of things which is advantages in PyTorch, which I found out, is this dynamic graphs, which is the way how these data structures are implemented, and as a result of which it has a much better memory utilizability. And the other point is that sometimes when we have very complex optimization, so when I will start teaching you adversarial learning, and there will be hashing examples, there will be multi-path adversarial learning or multitask adversarial learning, which will happen. So you will need to like slice of connections in a neural network. So it's like some part of the network is active, some part is inactive, some part will grow, some part will purge. All of these things will keep on happening when you are training the network. So over there, kind of dynamic graph structures are much more useful because they would actually kill the memory. They will not retain it. Whereas you can still implement them with TensorFlow. There is no issues with that. I mean, you basically mask off the activations from those layers. They still keep on activating, but so it's like you don't need the result, but you're still computing it out. So theoretically, it works out good, but for a practical purpose, we don't see a reason why we need to do it that way.
Sir, but TensorFlow also use the graph-like function, right?
TensorFlow uses what?
Sir, TensorFlow doesn't use like normal function. When we it's also compute graph like when I saw TensorFlow website.
TensorFlow does a data graph.
Yes, sir. Yes, sir.
Yeah. Data flow graph, DFGs, yes. And PyTorch does a dynamic graph. So dynamic graph is that the architecture of the graph can keep on changing. Signal flow graphs or data flow graphs are standard way. It's like pointer passing by reference. That's what I mean. Whatever you call in a high level language as a pass by reference, and for the data, that is what is actually called as a data flow graph or a signal flow graph in implementation parlance. Okay, let me start with what I wanted to do today. Wait, I have to share it right. Today is 9th of.
Excuse me, sir.
Yeah.
Sir, like I just want you, I'm requesting that, sir, please allow to Google Colab, sir, like, because for every epoch in my system, it is taking about 8 to 10 minutes to run. So even for 10 epochs, it is taking.
I am nobody to allow or disallow. I was just telling that it is not preferred to do it. So that you see, when you invoke Google Colab, you are not setting up the environment, you are not monitoring your processes, you are not environment as in not even the software part of it. Everything comes pre-packaged to you. So there it feels very nice, very cool, like you just start writing the code and everything works out. You don't even know what happens in the background on the compiler side of it. And there would be things which I would do in terms of profiling, which will not even work on Google. That was the reason of doing it. But otherwise, I mean, I don't have any such thing that I am anti-Google or anyone. You can do it on it, but the only point is that your learning experience is sort of like incomplete. You don't get the fun of these complications which come in.
Okay.
Okay, so today's thing is what we call as GoogleNet. Now, GoogleNet was what came right after VGGNet, and one of the reasons for bringing it was that it's equally powerful as a VGGNet, sometimes even more powerful than a VGGNet. But the only point is that the compute cost is significantly lower. Now, at the heart of this particular block, so this is a deep architecture essentially. Wait, is there an option I can paste the image? Okay, very good. There's an option, so let me do a thing. I'm trying to find a picture and paste it. But it doesn't come. The architecture is too big actually. I don't want to waste my time beyond for drawing it. I will rather use it from some. Yeah. No. Add image. Google. Oh, really weird.
Sir, I think you could also copy and paste the image.
This is really weird. I think I can also copy and paste the image. But I'm trying to avoid doing it right. I cannot copy and paste the image. I will still have to import it over here in order to paste it, to upload it.
So you could just press Control V to paste that, I think.
It happens on Google Slides. Here it doesn't happen. That's a problem. Yeah, I got it. I'm also learning. Don't worry. I'm not a pro at this Jamboard. I'm still trying to figure out all the features. Okay. Think now it's visible to all. Practically invisible to all. Not invisible in that great way. Okay, so let me go along with it. Now the point is that in this whole thing over here, if you look now, one is like it's a very deep architecture. Okay, your input goes over here. This input which you put down is typically a 3 cross 2 to 4 cross 2 to 4 input which goes down. It passes through, so there is a 7 cross 7 convolution. There is a max pool of 3 cross 3. Then there is something called as a what? Oh, local response normalization, local resp norm, and and then it keeps on going like this. So again, there is a convolution, then local response normalization, a max pooling, and then comes this block. Okay. Now this block has something interesting. So there are multiple paths through which your data is propagating in this particular block over here. There are like 1x1 convolution, there are 3x3 convolution. There is something called as depth concatenation, which essentially concatenates all of these channels together going to create a multi-channel tensor. Then again, that goes through these, and again you have this one. Now this block over here is what is called as an inception block. Okay, so GoogleNet gets its name as Google is for this Goog, and this is for Linet, and this was so because Jan LeCun had actually joined up Google in order to come up with this architecture over here. So you come to this depth concat, then you have a standard max pooling, which reduces the size of this tensor. And then again, you have this kind of a inception block working. Okay. Now, interestingly, you have this point which comes down over here, which is essentially a gradient injector. So what it does is you have some fully connected layers and you come up with a softmax activation over there in order to run a classification. Now, the purpose of this classification over here is, so typically for whatever classification problem you are solving, there will be this data which flows all through this depth and then comes over here in order to run this classification. That's my terminal layer of classification. But also one of the data flow is it will flow through here and come over here. Here also you can run classification. It will flow all the way through here and then come over here and run a classification over here as well. Now, as a result, what you have is you have these blocks which get exposed to a gradient which is coming from here. You will have these blocks which are exposed to this gradient as well as this gradient all through. These blocks which are exposed to this gradient, and this gradient. All the three gradients working out together over there. Now that is something which is interesting, which works out over here as to the number of gradients which would influence a certain block. Now, what we need to understand is about this particular block, which we called as inception. Okay, so wait. Okay. Now, what this inception block typically has is something like this. So you have a conf 2D of 1x1 and a stride of 1. Okay, so how do I write it? So this is, so I have actually forgotten how many. I think there are 16 convolution kernels over there. I'll have to check through that one, by the way, but I'm just putting it for the sake of it. Or just hold on, let me just check how many convolution kernels are there. I don't want to make a mistake around it. So this is 16C, 1W, 1S, 0P. Okay, so this is one block. Then you have another block which is conf 2D of 16C 1W 1S 0P. And then there is a max pool which is of 3W 1S. So whatever is your tensor over here, it goes to this, as well as now here there are 4 conf operators. So there is a conf 2D of 16C 1W 1S 0P. Then there is a conf 2D. This is of 16C 3W 1S 0P. Then there is a conf 2D of 16C 5W 1S 0P. And then there is a conf 2D of 16C 1W 1S 0P. This goes over here and this goes like this. Now whatever comes out from here, that runs into something which is called as depth concatenation. And then out comes your result. Okay. Now, if this block over here, so out comes your y. So this is x, this is y. Now, if that is the scenario, then can you tell me what? So if this tensor is r power of c cross m cross n. Okay. Can somebody tell me essentially okay, just a minute. This will have padding. This will have 1p. This will have 2p. Now can somebody tell me like what will be the size of the tensor at this location? So if this input is c cross m cross n, what will be the size of tensor at this location?
16 cross m cross n.
16 cross m cross n. Okay. At this location? At this location, what will it be?
That is also 16 cross m cross n.
Okay. And at this location? Oh, this max pooling will actually be with the padding as well. So this is 3W 1S 1P. Yeah. So and that would make that over here also you get a 16 cross m cross n.
C cross n.
C cross m cross n. Okay. Now this whole thing goes through this one and then out comes over here. It goes through this one, out comes over here. Now at this path over here. So what is the size of that tensor? That is also going to be 16 cross m cross n. At this location, what will be the size of tensor?
16 cross m.
Okay. So here also it will be similar. That is by virtue that there is a padding which is given in order to offset that one. And here also there will be the same size because this operator and this operator are of the same size over there. Okay. Now, typically there will be 16 channels here, 16 channels, 16 channel and 16 channels which come down over here. So in total, there is 16 into 4, which is 64 channels, which get depth concatenated over here. So this Y over here, the number of channels in this Y is going to be definitely how much?
64.
64.
64. Now, what will be the like other sizes over there? So the number of channels is 64, and what will be the spatial span?
M cross N.
M cross N.
M cross N. Okay. So typically, what you see is that within this inception block, the number of channels definitely changes based on whatever is given over here, and the spatial span through this operation is going to retain itself. Okay. So now if I look into this block over here, so whatever is the size of this input which comes from this max pool, there is the same of the size of this output which comes after depth concat. That passes through this one, which also gives you the same thing. However, this is the place where you have another max pool coming down over here. The moment you get this max pool coming down, so this is with a size of 2 cross 2 and a stride of size of 3 cross 3. So this is 3W 2S. So what that would do is that will make it 2 by 2 on both the axes over there. So as a result of which, this M cross N is going to become M by 2 cross N by 2. Okay. Now that again passes through this one. Now while it's passing through this, from here you basically curtail it up. So see, this is not part of the inception block. This is just a gradient injector over here. This is part of that inception block over here. So that's your inception block. This thing is just your gradient injector. So from output of this inception block, it passes through this one, and you have another pass of the gradient which comes from. Now you can look into whatever is the accuracy coming down over here, but that is not of great importance. I mean, in general, that accuracy is not going to be good. That accuracy is going to be bad over there. What did we gain as a result of it? So there are two things which happens. One is that if you look closely at these inception blocks, then the way these are made out of it, you see that there is a max pooling which is being brought out over here. Now, though it does not alter the size of the tensor because there is one S, then what do you think was the purpose of bringing it over here? So you have max pooling with a 3 cross 3 sized kernel, but the stride of that was 1. So what was the purpose, do you think, for bringing this one?
So as you earlier mentioned that we are preserving the intensities like higher activation.
Yes. So essentially over here, you are doing a mathematical morphological operation, and I'm nothing more than that. So all the high activations are being preserved over there. But the purpose is not to do any kind of a down sampling. So the frequency side is not getting compromised in any way. Okay. Now, yes.
So can you please repeat this? But I didn't get you, like the preserving of the higher.
So max pooling. See, max pooling with a 3 cross 3 sized kernel and a stride of 1. This is not reducing the size of the output in any way.
No, sir, it does not.
If my input is M cross N, my output is also M cross N. Okay.
Yes.
Then what is the purpose it is achieving? So what does it do? It stays at a point, looks into the 3 cross 3 neighborhood around it, and then whatever is the maximum value, it substitutes at that particular point. Now, is this similar to mathematical morphology operation by way of dilation? See, in dilation, what do? You do the same thing. So whether if there is a 1 or if I'm running it on a grayscale image, then within my span of that window, whichever is the highest value, I replace my central value with that value.
Okay, so we preserve the higher values, right, sir?
Yes.
Okay, understood.
Okay. So now, this is what this max pooling is doing. The next point is, then what is the purpose of these two 1 cross 1 convolutions? There are two such 1 cross 1 convolutions which I am using. What is the purpose of them?
Mixing information along channels, and preserving spatial,
Yeah. So you don't mix along the spatial dimension, you mix information only along the channel dimension. And then, so essentially what I did is I mixed along the channel dimension, and here I can mix both along the channel and the spatial dimension by way of over here. Now here we take a multi-resolution approach. So you have 3x3 you have convolutions with 3x3 sized kernels. You have convolutions with 5x5 sized kernels. So there are two such kernels with which it is done. And the purpose over here is to be able to mix across the spatial span in two different aspect factors over there. Okay, this is a much wider receptor field. This is a much narrower or shorter receptor field over there. Okay, now this together and this together make a block. However, if you see, these two blocks still implement only a channel mixing. So don't you think it should be possible that I can have these two blocks implemented only once and then I pass it multipath? But then I'm not doing that. I'm implementing this separately for this one. I'm implementing this separately for this one, instead of just there being one block whose output is passed on to these two blocks. Can you think of a reason why that is so pertinent? Why are we doing it in this way?
For space, like.
So to allow the weights to be trained separately for different paths.
Yeah. So for the first argument for space, this is going to consume more space. If you had just one block, it would be consuming lesser. Okay. Now for the second one, which is like for each of these weights to be learned. Now, why do you think that there will be different weights?
Because the different paths are coming from different sides.
So because the convolution layer before it has different the width of the convolution layer has is different. So the back propagation while updating the gradients, that information will be different in each passing through each of the convolution layer ahead of them.
So what you are telling me is an observation. Because you have two different blocks, so the gradients will be two different. Now, if I did not have two different blocks, I had only one block. If I had only one block, then both the gradients will pass through the same one. Then why do you think we are not doing it?
Hello, sir. Sir, like one thing regarding this, like if we take one block and do the operation and then just pass them on to the two separate convolutional channels, then will that lead to my output being 64 channeled?
See, there is a 16C, 1S0, 1W, 1S0P. There's the same thing. So this passes over here. Now here there will be 16 channels, here there will be 16 channels, here 16 channels, and here also 16 channels. And then this output will still be 64 channel.
Okay.
So when we will be updating our values, it will flow from right to left. So the convolution layer before the one we are trying to remove or we are trying to merge into one, these are different. These are different because one is 3. Okay.
So Hitesh, understand this one. Because I made them different, so there will be a different gradient flowing through each block.
Yes.
If it was the same, then it will be the same gradient. So say this particular tensor over here, that comes from some preceding part over here if you look into it. Now this is feeding to multiple paths. Now all the gradients of all the paths are going to come and influence this one.
Yes, sir.
So similarly, if I had just one block over here, then both of these gradients will influence that block.
Yes, sir. Got it.
But then you're not coming to an answer to my question, that why did not I have only one single block, but I considered having two different blocks?
So to identify more number of features like hidden, if we have more number of hidden layers, so we can identify more number of patterns and all.
So it's not about more number of hidden layers. Now the point is that you have a receptor field which is narrower, 3x3. You have a receptor field which is wider, 5x5. And anyways, this is the narrowest of the receptor fields over there. Now, essentially, what you have is that whatever pre-activations are required for this one to work out good should be something which is learned over here. Whatever pre-activations means what is coming as an input over here, and this is a post-activation, what goes as output. So whatever is relevant for this 5x5 span to work out good is what is being learned over here. So the inherent assumption is that the pre-activations best for this one and the pre-activations best for this one are different pre-activations. As a result, you need two different such pre-activation conditioning or channel conditioning layers which can work out good. So is that clear to you?
So can you repeat the last line? My voice was breaking.
So you have a 3x3, you have a 5x5. Now the kind of features this 3x3 is going to learn is very different from a 5x5, because a 5x5 has a much wider activation field than compared to a 3x3. If the fields are very different and the features are very different, now the nature of pre-activations it needs to be able to learn it is also very different from each other. So what that means is that what this learns is different from this. And then this is learning something which is very specific. This is a dimension which is very specific for this 5x5 controls. That's the reason why we have two different kind of channel mixer pipelines created over here.
Okay.
So these are reasons which the authors had given. However, till now, whatever we look over here and everything, this looks more of heuristic because there is no reasoning. Like, why should this be done in that way? Why shouldn't it be done in another way? That is not very clear to us. But this is, and you need to be very clear. Like, this is what we are speaking is something from 2010, 12, 14 kind of era. At that point of time, we did not have such mature knowledge in terms of neural architecture search and design philosophies going down over here. So that's the reason why it's much more complicated to understand, because what was the reasoning? They just picked it up and did. There were a couple of experiments which was done by playing around. In fact, like whether whether this max pooling should be inside the active inside this block or not, or should this max pooling should be coming before this dead concat or not, they were also considered over there. And finally, this is the most popularly used architecture for this inception block.
So is there any particular mathematical reasons to arrange the block sequentially like this?
It was again a heuristic designer's prerogative. Even in VGG, if you tell me, they did say like, okay, this was why we arranged it. But then there are also many other possible ways of doing the same thing in order to achieve it. In fact, when we do neural architecture search, I'm going to show you exactly like in some other arrangement also, you will have the same kind of compute which will be coming up.
Okay, got it.
Hello, sir.
Yeah.
Yeah, sir, like in one thing you just said that the kernel size in Cont2D, like the second one is 3W, or like it's a 3x3, and in the next one is 5x3. So we are defining two different channels in order to prepare the data for two different kernels, right, sir?
Yes.
So like, sorry, like what difference is there? Like what is the different thing that we are doing in the second thing that is not being done in the first one? Like what are we actually preparing the data? Like it is a 16C1W in both the cases. Like what is different being done in both of them?
Oh, that's what I'm saying. So it's 16C1W, but the number of convolution kernels are different. So it's like this. There are 16 convolution kernels which are very unique, and they will be tuned according to the requirement of this block. Similarly, these will be tuned according to the. So the gradient passes like this. So this gradient is coming from here, then influences this one. So based on the output generated by here and whatever is its contribution to the error, this one will get modified. Hey, just a minute. Hello. And over here, this gradient which passes through here based on whatever is the constituent over here is going to influence this one.
Okay, sir. Okay. Okay, so that is what you meant when you said that we are preparing the data for those commands.
Yes.
Okay.
And the nature of output generated by these blocks is very different. So this one's output is different from this one's output. That's why the gradient which goes and influences this one is very different from the gradient which goes and influences this one.
Okay, sir. Okay. That is why they are required separately.
Yes.
Sir, may I ask one thing, sir? Like what you told and whatever we have discussed, I'm getting the feeling that say I want to detect a small ball and a large ball. Say. Then the con 2D before that the smaller kernel
This will be more of like receptive to the small ball. This will be receptive to the larger ball.
Yeah, so like we are not detecting in a single one, like a different size ball. We have a set for this size ball. This will be the one. Okay.
So I mean, these come down from what we call as theory of resonance in filters in case of signal processing. So it has its root in terms of resonant theory of signal processing.
Okay, sir.
Okay, guys, then we close for the day over here. So tomorrow I will actually, I wanted to do neural architecture search a bit later, but I think now you guys are at the right time. Before we get into the backpropagation and hyperparameter, I will rather introduce you to the neural architecture search, which is still a problem to do with architecture and the forward pass of it. So the first thing which I will start with tomorrow is I will bring forward to you two different architectures. In fact, like we will derive them in the class, two different architectures which will have the same compute cost. And that will lay our basis of finding like how can we now work subsequently towards it. Okay, so.
And so one more thing, sir.
Yep.
Hello. Yeah. So like we are defining 3 softmax functions, right? So like at each layer. So like now my understanding